In this video, we are going to compute the double integral of the function 4y e to the x over the triangle given in the picture that you see on your screen. And you can see that I've already somewhat, well, I haven't set up the integral officially, but I have made one selection so far. I've decided to integrate the inner integral with respect to y. Now you might ask, why have you done that? How can you know already that that's the right way to go? And the short answer is that I don't, but I'm making an educated guess that this will be easier, that this will be the most efficient way, because the lines that determine our region here, we know how to find the equations of lines best in terms of y's, right? So when we find these equations, we're going to have y equals something in terms of x, an expression in terms of x. That's how the point-slope formula or slope-intercept form, they are all of the form y is equal to, and so I'm just making a guess that that's going to be the right way to go. Anyways, let's go ahead and do that. Both of these lines go through the origin, it should be noted, so they're all going to be of the form y is equal to slope times x. Normally, of course, we would have the plus b, but they all go through the origin, and so the plus b is just plus 0. So all we need to know are the slopes of these two lines. Let's see here. Let's do this line first, outlining it in red here. So let's see. We have a change in x, or a run, of 4, and we have a change in y, or a rise, of 1. That gives us a slope of 1/4. Okay, so that is our red line right there. Let me erase some of this stuff. Now let's take a look at, I don't know, the green line. Sounds like I'm giving somebody directions on the subway. Okay, so here we have a run of 4, a change in x of 4, and a corresponding change in y, or a rise, of 3. So the green line has equation y is equal to 3/4 x. Okay, so far so good. All right, so essentially what that tells the integral is that, well, if we want our, let's set up our inner integral here. This says that we want to integrate over the region from y is equal to 1/4 x to y is equal to 3/4 x. Okay, now the problem, and the reason that we're not done setting up the integral yet, is that, well, we only want this one particular triangle, and right now, what the integral understands is that we want potentially all possible area enclosed between these two lines, and we certainly don't want that, right? We just want that one triangle right here, the shaded triangle. So let's not lose sight of that. So to tell the integral that we only want the shaded region between these two lines, well, the outer integral is with respect to x, so we say, all right, well, hey, we want only to take the area between x is equal to 0 and x is equal to 4. And there we go. We have set the integral up. All right, so now let's take a look at evaluating our inner integral. Let's evaluate our inner integral. Because it's with respect to y, I'm going to pull e to the x out front, because, after all, with respect to y, with respect to the inner integral, e to the x is just a constant. So we're integrating from y is equal to 1/4 x to, y is equal to 3/4 x. And the function that we are integrating is 4 times y dy. All right, so e to the x is going to stay on the outside. The antiderivative of 4y is 2y squared, and we want to evaluate this from y is equal to 1/4 x to y is equal to 3/4 x. And there I've plugged all those in. It occurs to me that a reasonable question that you might have at this point is, if you pulled e to the x out to make the integral easier, why didn't you pull the 4 out? And that's a good question. The reason I didn't do that, it was intentional. It was to avoid getting the fraction. So if we had just taken the antiderivative of y, that would have been y squared over 2, and it would have introduced a 1/2. And I didn't want to have to deal with that just yet. Anyways, moving right along. And I'm going to do some algebraic manipulation for us here and save us some time. What the inner integral simplifies to is x squared e to the x. Now, sometimes when you get to this part of a problem, when you get to the outer integral, you're going to look at the outer integral that you have created for yourself and realize, oh, geez, I should have integrated first with respect to x, or with respect to insert other variable here. And this certainly does not look like a very nice integral. So I'm going to plow ahead because sometimes you just end up with unpleasant integrals no matter which way you slice it, and you have to soldier forward anyways. And plus, I already know ahead of time, I've done the legwork and worked this one out. But my main point in bringing this up, okay, I have a reason for almost all of the things that I bring up in these videos, and the reason here is that it's perfectly acceptable to want to go back and say, okay, well, this integral looks difficult. Why don't I go back and try integrating first with respect to x? That's a perfectly legitimate move. I do it all the time. I'm pretty sure anyone who spends any amount of time evaluating double integrals does the same thing. So feel free to do that. Now, the trick that you need here, okay, we are not going to rehash this integration technique in this video. What you need is, I believe, let me look at my notes real quick. Yes, you have to, I believe, do 2 iterations, 1, 2, yes, 2 iterations of everybody's favorite integration technique, integration by parts. Okay, so if you do that 2 times, what you find is that the antiderivative of x squared e to the x is this expression here. And then if you evaluate this at 4 and subtract this expression also evaluated at 0, well, what you'll find is 10 e to the 4th power minus 2. By skipping some of these steps in this video, I do not mean to suggest that these steps are easy. I don't mean to suggest that they're not important, just simply that I want to focus as much as I can on the conceptual aspects of multivariable calculus rather than spend, say, 13 minutes with a massive amount of algebraic manipulation. Okay, so the point here, in other words, is not to learn integration by parts. You already know integration by parts. The point here is not to combine algebraic expressions, it's to do multivariable calculus. All of which is to say that you should work these parts as an exercise and make sure that you know how to do them, because some of these, I might not ask you for a problem that involves 2 iterations of integration by parts on an exam, but certainly you could see integration by parts, and certainly you will see problems that involve a large amount of algebraic manipulation. And if you haven't done any of those on your own, then that will unfortunately and most likely create problems for you on the exam, which both of us, I think, would rather avoid. Anyways, the key part, circling back, the key part of this problem, as I see it, is not lengthy discussions of integration by parts and algebraic manipulation, but instead the setting up of the integral. So we were given a picture of the region of integration, okay? We found the equations that determined the region, okay, equations of lines, and then we used x equals 0 to x equals 4 to narrow it down so we didn't catch all the area trapped between these 2 lines. And we went from there. We had to set this integral up ourselves, which in a lot of these problems is really the hardest part. So if you understood that part, and you've gone through and you've done the legwork and worked through the integration by parts and algebraic manipulation, then you should be in good shape. Congratulations, job well done.